So welcome to this class. In this section or in this short session, we are going to discuss about cross product. So we'll define what a cross product of two vectors is, and then list a few properties of cross product. And then the next session we'll do some examples on cross product. So the cross or vector product cross or vector product. So as usual, we start by defining what we mean by a cross product. So let A and B be vectors. Then the cross or vector product of the vectors A and B is another vector C, which is written in this form: A cross B, given by so this vector C is given by A cross B equals to magnitude of A times magnitude of B, then sine theta, and then times U, where theta is the angle between A and B, is from 0 to 180 degrees. And then this U is a vector determining the direction of A cross B. U is a vector indicating, actually it's a unit vector. It's a unit vector determining the direction of A cross B. So that's how we define the cross product of two vectors. So properties of cross product. So let A, B, and C, the three vectors, and M be a scalar. Then one, A cross B is negative B cross A. So commutative law for cross product fails. So when you change the order, you get a different vector. Commutative law for cross product fails. Changing the order give a vector which is in the opposite direction to the original vector. And then number two, A cross B plus C is the same as A cross B plus A cross C. So this one is distributive property for cross product. Property or law. And then number three, if you take a scalar and then multiply by the cross product of two vectors A and B, then it's the same thing as taking the scalar multiplied by vector A and crossing the result with vector B, or taking vector A, you cross with this scalar multiplied by vector B. Or you simply take the cross product of A and B, and then finally multiply by this scalar M. Number four, now if you draw this 3D Cartesian plane, so this is the Z axis, this is the X, and then this is the Y. So we use this right hand to show the direction of motion and how to carry out the cross product. So we know that here we have, this is the I along the X-axis, and then this is the J along the Y-axis, and then we have this is the K along the Z-axis. So we're using the right hand to describe the motion or the directions in which the cross product should be applied. So from I, you go to J, and then from J, you go to K, and then from K, you go to I. That is the direction we need to pick. So when you say I cross J, then you get, so this is the direction. From I, J, then you get this K. And then J cross K. So j cross k, you get now this vector I, and then k cross I, k cross I, then you get this vector j. So those are the positive directions. But now when you reverse the direction from the first property, so commutative property fails, if you get now j, you cross with I, so j now, if you now change the direction, that you get the negative, so negative k. And then k cross j, you get negative I. And then I cross k, you get negative j. So the cross product is very sensitive to order. And then if you are getting I cross I, you get 0 vector. J cross j, you also get 0. And also k cross k, you get 0. I remember, so because they are vectors, we show by this. So this is because we are defining the sign of the angle between the two vectors. So angle between I and I is 0 degrees, sine of 0 is 0. So that's why these are 0 vectors. So it is different from the what we saw in the dot product, whereby if you are dotting vectors of the same kind, you get 1. But for this case, you get 0. Number 5, if vector A is given by A1I plus A2J plus A3K, and vector B is given by B1I plus B2J plus B3K, then A cross B can be written as a determinant of I, J, K. And then the second row, you write the components of the first vector, this A. So we have A1, A2, A3. And then the last row is the components of the vector B, B1, B2, B3. So similarly, you can define B cross A as B cross A will be given by the determinant of I, J, K, and then you write B1, B2, B3, A1, A2, A3. So which means that the cross product of two vectors A and B can be written as a determinant. So in the next session, we'll show how this one is obtained. And then 6, the magnitude of the cross product of two vectors A and B is the same as the area of a parallelogram with sides A and B. Sides given by vector A and vector B. And lastly, number 7, if the cross product of A and B gives you a 0 vector, and both A and B are not null vectors, then A and B are parallel. This is because we have defined the cross product of A and B to be given by A cross B, magnitude of A, magnitude of B, sine of theta, and then a unit vector determining the direction of A cross B. So when A and B are not null, so this is non-zero, this non-zero. So which means then 0 must be obtained from this point here. And then sine theta equals to 0 implies theta equals to sine inverse of 0. And this is only possible when angle is 0 or 180 degrees. And then 180 degrees is what makes or what defines the two vectors being parallel. So that's the end of the first session. So in the next session, we'll give examples and some of proofs involving the cross product. So thank you.